We are living in a digital age. Significantly, this is also an age when we are poised to leap forward to an exciting and mind-boggling era of revolutionary changes in science and technology, most of which we can attribute to supercomputers. Astrophysicists use supercomputer as time machines to explore the past and the future of our universe. Researchers can determine the shape of a molecule's surface and generate an atom-by-atom picture of the molecular geometry. Closer home, every year there are cyclones in and around coastal areas, and floods in areas located near rivers play havoc, and as a result, millions of lives and properties are lost. However, with the advent of each generation of supercomputers, prediction of such and other disastrous events is becoming more precise, giving adequate advance warning for the administration to get those areas evacuated. And all this is only the tip of the iceberg. But then, how does a supercomputer help manage to do so much? And how is it different from your desktop PC and laptop? Let us find out. The personal computers of today are generally designed for looking at documents, pictures, and videos. As such, they have matching accessories and features. Also, on an average, 1 TB of data that they can store is adequate for a few 100 million to billion operations per second. In contrast, modern-day supercomputers are built for very large operations with a cumulative memory of multiple petabytes. So, in place of one processor of a PC, it has 2 or 4 per node, a couple of dozens of nodes per cabinet, and then tens to hundreds of cabinets as a cluster, each containing several nodes, several multi-core sockets, all interconnected with a vast network of cables. A node is similar to a standalone computer, where theoretically you could pull one out, hook a screen and keyboard to it, and have a powerful PC for use. The configuration of this order makes a supercomputer so powerful that it can provide researchers with insights into phenomena that are too small, too big, too fast, or even too slow to observe in laboratories. But to run these supercomputers 24/7 for large calculations, the processors consume huge amount of power, and that heats up the system considerably. Therefore, to run them efficiently, you need a good deal of infrastructure for providing power and cooling. A typical supercomputer of 1 petaflop capacity would require a few hundred kilowatt of power and around 100 tons of cooling. Another fact about supercomputers is that people don't usually need the whole of a supercomputer, and as such, the machine is shared. That means that there is a front end with login nodes where you compile and submit batch jobs to the computer nodes and then let the computer finish the job. Basically, a supercomputer is designed for computing and crunching numbers. To undertake this exercise, it breaks up its task across many processors. For this, supercomputers focus on floating point arithmetic that is needed for very large or very small real numbers or computations that require a large dynamic range. This is very similar to scientific notations in a calculator, except that these are carried out in base 2 rather than base 10. Here, the speed of calculating the data is measured in flops, that is floating point operations per second. Modern versions of supercomputers are capable to handle exabytes of data at speeds of teraflops. While talking about supercomputers, we often also tend to hear the term high-performance computing or HPC. Technically, a supercomputer is a system that performs at or near the currently highest operational rate for computers. HPC is an application by supercomputers to deal with computational problems that are either too large for standard computers or would take too long. While often using custom-made components, it is especially applicable to systems that function above a teraflop or a petaflop. The most common users of HPC systems are the scientific researchers, engineers, and academic institutions. HPC provides the means to actually perform complex calculations enabled by science, and hence every forecast and prediction relies on these HPC resources. It is absolutely central to weather prediction systems. The history of supercomputers in India dates back to the mid-1980s, when the government of India decided to acquire supercomputers from USA. Bottlenecks in such acquisitions proved to be a blessing in disguise, and this threw up a challenge for indigenous production of supercomputers within India. The newly formed CDAC took up this challenge and went on to produce a series of Param supercomputers between 1990 and now, the final one being Param Yuva II, that has an impressive configuration by any standards. CDAC has commissioned and operates 3 national computing facilities for HPC users community in India for a wide range of intensive tasks across a wide range of disciplines. So with these machines firmly ingrained into our institutions and even our social fabric, it was an excellent time to wonder about the future. Will the next decade and beyond see the same kind of spectacular progress as the previous ones? It was acknowledged that in order to increase the accuracy of forecasts, higher resolutions and more accurate simulations of physical processes are required. A brainstorming on this aspect by the leading policy-forming institutions within the country formed the backdrop in the formation of the National Supercomputing Mission in India. NSM brought together the best minds within the country on one platform to constitute its mandate and strategize the modus operandi to achieve its goals.
We began at the gigaflop, which is performing billion instructions per second, went on to build trillion supercomputers that can perform trillion instructions, and now we are at the peta level, this one, 1,000 times the trillion, this one. But our objective, in fact, I think the whole world is trying to build systems which can really go to the exascale, 10 to the power 18 mathematical operations per second. That's the kind of systems which we are trying to build. The NSM mission is to build such systems actually. Build it indigenously, means from the Indian, starting from the chip level to the systems level and their applications, and make it widely available to the people of India.
The main purpose of this is to provide a grid of supercomputers to the research and development in the country.
This was a very highly, innovative and very highly foresighted project, initiated initially by the Department of Science and Technology. The Ministry of IT also joined us, so the 2 ministries together have been handling it.
This project is implemented by CDAC and IISc. Even major IITs, NIITs, central universities, research labs and industry is synergizing to deliver the world-class state-of-the-art solutions.
Indian Institute of Science became the window to the academic world to actually translate its dreams about supercomputing into the NSM project. And CDAC, it has a core strength in application development and also in human resource development.
Yet another goal of CDAC was to design, develop and deliver the indigenously built supercomputer and its components, which includes server class motherboard, system area network, parallel storage system and even HPC processor.
In the process of the formation of NSM, the Indian needs in supercomputing as well as the manufacturing capabilities of Indian agencies was mapped. The requirements of manpower for the development of supercomputers and systems as well as scientific computing software were also assessed. At the same time, the major areas that need supercomputing power and the grand challenge problems of national and international relevance that need to be solved in each of these areas were also identified. As a strategy, the implementation of NSM was taken up at 4 levels: supercomputing facilities and infrastructure setup, application development, research and development, and human resource development. NSM was set up with the intention of creating a roadmap for India's growth as a superpower. In this direction, to start with, 70 world-class supercomputers would be installed in institutions across the country through a combined approach of assembling, buying and manufacturing. The strategy employed to achieve this ambitious task would be through 3 phases that will run concurrently. Phase 1 will involve indigenous assembly of supercomputing systems using components. Phase 2 will involve manufacturing supercomputing systems in India. And the Phase 3 will involve complete design and manufacture of supercomputing systems in India. In the first phase, 6 institutions will benefit. Out of these, 2 computers will be of 1.3 petaflops, the remaining of 650 teraflops. System software stack as well as the design and development of the supercomputing systems will be developed indigenously in all the 3 phases of the build approach. Ultimately, they would all be connected together through the National Knowledge Network such that the benefits may be accrued by all.
HPC Interconnect is also indigenously built by CDAC with 2 variants. The first one is 4x6, that is 240 gigabits per second, and the next one is 100x6, that is 600 gigabit per second, which will be deployed in the supercomputing systems.
In addition to this, we have a cloud which we are going to build, which will be attached to this, where all the softwares which will be developed as applications are going to reside. The software systems which will be used by the supercomputers will also reside on the cloud.
Another milestone will be a special purpose machine for various applications. Here we are going to work on developing Monte Carlo algorithm in hardware, which can be very effectively used for molecular dynamic applications. Another SPM is the cryptanalysis system.
It is not the computing power of a supercomputer that makes it a great tool, but the key lies in how and where this power is applied. It was decided by the NSM team that the applications have to be of local relevance and must also compete with the global capability. The application framework developed under NSM, therefore, aims to serve as a user-friendly platform for the scientific community. A team of developers and experts will be made available to the users for hand-holding and benchmarking for attaining higher performance in their domains. NSM outlined several key development areas for India-specific applications. Applications related to computational chemistry, computational physics, and integrated applications in health are being developed in collaboration with several other institutions. The Indian Institute for Tropical Meteorology is working on applications on weather forecasting. Another application is on simulation of floods in metro cities, aiming to tackle and reduce its impact. An application on computational astrophysics is another key area where India has taken the lead in the world. In addition to this, the application on geophysical exploration is being utilized by ONGC and other petroleum companies. NSM is extensively working in cancer research with Tata Memorial Hospital and AIIMS. The drug repurposing project is targeted towards the reduction of time taken in clinical trials for prescription of drugs. Also, the drugs used for diabetes is showing very good results for breast cancer.
So the National Supercomputing Mission, in that sense, seeks to bring in different parts of biology together. Structural biology in terms of the protein data bank, genome databases which come in from the part where you have high throughput sequencing data and all of this data is assimilated into one data set. Computing resources. Now that's very important because biology is all about movement, it's about dynamics. If I'm so static, I really don't tell you what I really mean. So biology and biomolecules essentially do the same thing. And dynamics comes from computational resources, high-end computing. So this is where all of this part is being put together as a part of a national cluster. This would bring in people from academic environments, universities, institutions, large setups, companies even. All of them get together to be able to use this national resource.
R&D under NSM aims to enhance indigenous content in the systems to be delivered in build model.
The main objectives of the NSM R&D expert group is to identify and initiate key research areas that are essential in exascale computing. It would also look at the frameworks and components that are needed. It would identify the developments that are happening in these areas, update a NSM Technical Advisory Committee. It would solicit project proposals in various areas, evaluate them and recommend them to the NSM Technical Advisory Committee. It would also evaluate and monitor the progress of these projects as and when they are taken up. There are several research areas or components that we are looking at. These are broadly classified into system architecture, system software including scalable algorithms and libraries, and data center management.
The R&D activities to be executed will cover within its scope interconnection network, as it is an important and critical component of an HPC machine. Without this component, a parallel machine cannot be realized using computer nodes. It is proposed to develop an indigenous high-speed interconnect network to address this. In the area of system architecture, NSM is looking at problems like HPC application or workload characterization, power and performance estimation methodologies. Another area of concern is middleware for HPC that deals with scheduling and checkpointing recovery, as large-scale supercomputing systems involve several thousands of computing nodes. Problems relating to data management software for big scientific applications are being looked at to address storage and parallel file systems.
In the area of data center infrastructure, we are looking at problems of defining efficient data centers for mid-range and high-end computing systems. We are also looking at models and tools for heat flow in data centers and smart management of system cooling.
Current work is on for the development of tools for parallel application performance, programming models, languages, compiler, middleware, HPC application framework, and POC implementation of silicon photonics based transceiver module.
We have defined each project to have a definite deliverable. That is the primary criteria for the evaluation and selection of these projects. The outcome of these projects could be in terms of software frameworks like a simulator, or could be software packages like a compiler tool or a performance evaluation tool, or it could even be a debug tool that could be provided as a part of the project. We are also looking at projects which will deliver software libraries for specific application domains.
But when you look at all of these things, you suddenly realize you don't have the kind of manpower that's needed to run these supercomputers, and also utilize them optimally. And not only that, but also design algorithms that would run more efficiently on these supercomputers. So an HR initiative, Human Resource Development Initiative, is also part and parcel of this.
The mission envisages manpower development in areas of high-performance computing applications, parallel programming, and HPC system administration and management. The objective is to develop at least 20,000 HPC-aware experts and professionals with capability in supercomputing. This will be done through planned collaboration between R&D organizations, academia, and the industry. The planned activities of NSM Expert Group HR development includes curriculum development and content creation, train the trainer model for multiplicative effect, conducting workshops and seminars for HPC awareness, use of various training methods like classroom and e-learning, providing access to state-of-art hardware platform for training, which will be accessible from all over the country, and offering fellowships to PhD students. Training courses have been designed in such a way that there are courses for pure computational people as well as for people from non-computational multidisciplinary backgrounds but who may have yet worked on any HPC-related project. Today, the role of the government to fulfill critical missions in national security and breakthrough science has become crucial. What are the expectations of the beneficiaries of NSM from this perspective? Let us find out.
We work on computational chemistry and computational biology, and specifically we are studying industrial solvents which catalyze organic reactions. And a better representation of lipases would help us a lot, and in this domain the arrival of National Supercomputing Mission petaflop scale machines would help us do these problems, attack these problems much more realistically.
We want to make new materials that don't exist in nature, and it's been estimated there are about a million possibilities to explore. This is just a huge number to explore, and you can't try out so many different combinations in a laboratory, in an experiment, in a factory. So that's why we need supercomputers.
Most technologies take 20 years to mature from the discovery of a key material to deployment of the technology in real applications. Computer simulations can shorten this span of time, leading to very important discoveries of materials in a timely manner, and also reduce the cost associated with it.
I deal with systems which has higher number of atoms, which is very difficult to simulate with the present computational facilities. So if we have a supercomputing facilities, those simulations will become very fast and very accurate, which will have very high impact on the pace of science and technology.
There is an ongoing research on the possibility of converting carbon dioxide into useful chemicals. In achieving this, the first step would be to capture carbon dioxide present in the atmosphere or which is released from the coal fields, which is called carbon dioxide sequestration and storage. I model materials which can capture in itself carbon dioxide as much as its own weight, and modeling involves using fundamental forces of nature which can be more realistically represented in computers with higher computing power.
The key proposition of NSM is that if India is to be a world leader, it must continually work towards establishing world-class HPC ecosystems of talent, technology, software and infrastructure. The ability to manage the massive data generated and to perform modeling, simulation and analysis will determine the products, industrial processes, business models and industries of the future. Industries will then also have a platform to think big and apply advanced computational methods to become globally competitive. This will in turn lead to breakthroughs in diverse commercial applications along with the optimal development of energy resources. This thought is at the heart of this mission.